Assalamu alaikum. Welcome, dear students, to the second part of Chapter 11 about the refraction of light. By the end of this video, you will be able to state and apply the laws of refraction of light, or Snell's law of refraction. We will start by having a quick revision for the ideas of the previous video. We've studied that refraction of light is the passage of it between two transparent mediums where its speed changes. Also, we've studied that in optics, each medium is characterized by its index of refraction n, where n is the ratio of the speed of light in vacuum to its speed in the corresponding medium. The index of refraction is always greater than or equal to 1. It is unitless, and the index of air is approximately equal to that of vacuum, which is equal to 1. It's important to notice that between two transparent mediums, the one with the larger index of refraction is called more refractive medium or optically denser medium. And as light passes to a more refractive medium, each refracted ray bends toward the normal, where the angle of refraction is always smaller than the angle of incidence. Whereas when light passes to a less refractive medium, each refracted ray bends away from the normal, where the angle of refraction is always greater than that of the angle of incidence. Now let's observe the following phenomena. When you stand in front of a window or look at the surface of rest water, you can see yourself even though the window and the water are not mirrors. They are transparent mediums that light can pass through. Actually, a part of light is always reflected, which means that the refraction of an incident beam of light is always accompanied with a partial reflection of light. Then, when a light ray strikes the interface of two mediums of respective indices n1 and n2, the elements of the refraction diagram are as follows. The incident ray Si, the angle of incidence I1, which is the angle between the normal and the incident ray, the reflected ray IR prime, and the angle of reflection R, the refracted ray IR, and the angle of refraction I2. But what about calculating the exact measure of the angle of refraction? Let's now use the following simulation to try to establish a relation which allows us to calculate the angle of refraction I2. Here we have a laser light, and here we can choose the two mediums where light propagates. The first medium is by default air of index of refraction 1. We will choose a glass in the second medium, whose index of refraction is 1.5. Then, in this case, light will propagate to an optically denser medium where its speed slows down. Now we will send a light ray. We can note the incident, the reflected, and the refracted ray. The reflected ray is dimmer. Using the intensity light meter, we can clearly see that the intensity of the reflected ray, which is 9.19%, is much smaller than that of the refracted ray, which is 90.81%. That's why we say that a partial reflection is always accompanied by the refraction of light. Now we will try to find a relation between the angle of incidence and the angle of refraction. We will use the protractor to record some angles. When the angle of incidence was 0 degree or is 0 degree, the angle of refraction is 0 degree. For I1 equal to 20 degree, I2 is equal to approximately 14 degree. For I1 is equal to 30, I2 is equal to 20. For I1 is equal to 40, I2 is equal to 25. These values are tabulated in the next slide. But in this case, where light propagates from less to more refractive medium, we can clearly notice that regardless the increase in the angle of incidence, it is almost close to 90, refraction of light always takes place, and each refracted ray bends toward the normal, where the angle of refraction is always smaller than the angle of incidence. The previous values are tabulated in the following table. Let's calculate the sine of the angle of incidence, the sine of the angle of refraction, then calculate their ratios. Sine 30 divided by sine 20 gives us 1.46. Sine 40 divided by sine 25 gives us 1.52. Similarly, we will obtain 1.53, 1.509, and 1.501. We can notice that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is approximately equal to 1.5, which means that it is constant, where this slight difference is due to experimental error. On the other side, let's pick out the indices of medium 1 and 2. They are respectively n1 equal to 1 and n2 equal to 1.5. Now let's calculate the ratio of the index of the second medium to that of the first medium. We will obtain 1.5. By comparing the results, we can notice that the ratio of the sine of the angle of incidence to that of the sine of the angle of refraction is equal to the index of the medium of refraction divided by the index of the medium of incidence. This relation is the second law of refraction, known as Snell's law for refraction or Snell's-Descartes law. Then, the second law of refraction or Snell's law of refraction, which is sine I1 divided by sine I2 is equal to n2 divided by n1, can be expressed as follow. n1 times sine I1 is equal to n2 times sine I2, where n1 is the index of the medium of incidence, I1 is the angle of incidence, n2 is the index of the medium of refraction, and I2 is the angle of refraction. But what about the first law of refraction? Let's observe the following experiment. We will use a source of laser light, a tank half filled with water where light can cross the interface air-water and the refraction of light takes place. We can observe the incident ray, the refracted ray, and the point of incidence. Using a sheet of paper perpendicular to the interface, we can prove that the incident ray and the refracted ray exists in the same plane of the paper, called the plane of incidence. Even when we change the position of the tank and the light is still directed coincident with the plane of the paper, you can still see the incident and the refracted ray in the same plane, which is that of the paper. Then, the first law of refraction states that the incident ray, the refracted ray, and the normal at the point of incidence all lie in the same plane called the plane of incidence. Let's materialize the first law of refraction. Here we have the surface of separation between the two media. This is medium 1 and this is medium 2. Here we have the normal, which is an imaginary line perpendicular to the surface of separation. The first law of refraction states that the incident ray, the normal, all lie in the same plane of incidence with the refracted ray. But also in chapter 8, we've studied in the first law of reflection that the incident ray, the normal, and the reflected ray all lie in the same plane. Then, the three rays, the incident, the reflected, and the refracted ray with the normal, all lies in the same plane of incidence. Then, the first law of refraction states that the incident ray, the refracted ray, and the normal at the point of incidence all lie in the same plane called the plane of incidence. The second law of refraction, which is Snell's law of refraction, states that the ratio of the sine of the angle of incidence I1 to that of the angle of refraction I2 is constant. This relation can be represented as sine I1 divided by sine I2 is equal to n2 divided by n1, or n1 sine I1 is equal to n2 sine I2. Let's consider now the following special case. If we adjust the incident ray so that it strikes the interface normally along the normal, when measuring the angle of incidence and its corresponding angle of refraction, you will notice that both of them are 0, which means that in this case refraction took place but without any deviation. If we observe the wave instead of the ray, we can notice the change in the wavelength due to the change of speed upon passing into another medium. To verify this result by calculation, If I1 is equal to 0, then sine I1 is equal to 0, and 2 could not be equal to 0, then sine I2 is equal to 0, which gives us that I2, which is the angle of refraction, is equal to 0 degree. Let's practice now by performing the following application. Don't forget to pause the video and try to perform the application by yourself. Light traveling in air is incident on the surface of a block of transparent plastic at point I at an angle of incidence of 62.7 degree and is refracted in plastic of index and P equal to 1.18. Indicate the two phenomena that take place. We have the refraction and the partial reflection of light. Determine the more refractive medium and specify if the light bends toward or away from the normal. Since the index of plastic is greater than the index of air, then the plastic is more refractive medium. So the light passes to a more refractive medium and it will bend toward the normal. Now you are asked to calculate, naming the used law, the angle of refraction in the plastic. Here we will use and apply Snell's law of refraction, where the sine of the angle of incidence divided by the sine of the angle of refraction is equal to the index of the refractive medium, which is Np, divided by the index of the incident medium, which is Nair. Then sine I2 is equal to Nair divided by Np times sine I1. This gives us, after substitution, 0.752. Now to calculate the angle of refraction I2, we use sine minus 1 to the obtained value on the calculator, which gives us 48.7 degree. Let's draw now the incident, the reflected and the refracted ray at I. We start by drawing the normal at the point of incidence I. Then, using a protractor, we draw the incident ray at an angle of incidence 62.7 degree from the normal. Then, using the laws of reflection, the angle of reflection R is equal to the angle of incidence I1. Then, also using a protractor, we draw the reflected ray at an angle of reflection 62.7 degree from the normal. Now to draw the refracted ray, we draw it in the part of the medium of refraction which is opposite to the incident ray, which means in this case it is drawn in this part. We have calculated the measure of the angle of refraction and it was obtained to be 48.7 degree. Then using a protractor, we draw the refracted ray. Now you are asked to deduce the angle of deviation D, which measures for us the deviation in the ray's direction upon passing into another medium. Actually, the angle of deviation is equal to the difference in the angle of incidence and the angle of refraction. In this case, when light passes to a more refractive medium, since I1 is greater than I2, then the angle of deviation D is equal to I1 minus I2, which is equal to 62.7 minus 48.7, which gives us 14 degree. Now, in this part, we have studied the two laws of refraction. The first law states that the incident ray, the refracted ray, and the normal at the point of incidence all lie in the same plane called the plane of incidence. The second law of refraction states that the ratio of the sine of the angle of incidence I1 to that of the angle of refraction I2 is constant. In the case of normal incidence, where I1 is equal to 0, the ray refracts undeviated at an angle of refraction I2 is equal to 0, and as light passes to a more refractive medium, it refracts towards the normal and the angle of deviation is D equal I1 minus I2. Thanks for your attention. This is the end of part 2.